So, welcome to the first chapter in this exciting journey of becoming an accomplished chemist. And in this chapter, we will be looking to answer the question, what is chemistry? Chemistry is a science of matter, both its property and how it reacts with other matter. It is a branch of science that deals with the study of the composition and reaction of matter. Chemistry is a physical science, which means it focuses on things that are not living. Instead, chemistry, just like other physical sciences, studies the laws of nature. It is considered to be one of the fundamental sciences because everything in the universe obeys these natural laws. Chemistry answers the question, what is it made of? And the answer helps us to understand how a substance will behave under given conditions, such as changes in temperature, light, and pressure. Chemists are also interested in how atoms join in chemical bonds and how they can be broken apart. When most people think of chemistry, they think of elements. By 2012, chemists had isolated 118 different elements and organized them in what we call a periodic table. People have been studying chemistry for hundreds of years. Famous chemists include Marie Curie, known for her research in radioactivity, and John Dalton, whose work is fundamental to our understanding of the atom. Chemistry is used everywhere, every day. It is used by pharmacists to create new medicines, by police in detecting crime, and even by engineers to make chips powering the computers you are using to watch this video. In chemistry, all substances are collectively known as matter. So let's start by understanding this term, matter. When you look around, everything in and around us is made up of either three things: solids, which we can see, smell, touch, and even taste; liquids, which we can also see, smell, touch, and taste; or gases, which we mostly can't see or touch, but we can feel their effect, although a few can be seen or even tasted. So what do liquids, gases, and solids have in common? They are all made of matter. Matter is anything that has mass and occupies space. In other words, it has mass and volume. You might be wondering why they look so different if they are made of the same thing. But the truth is, all things are made of matter, just in different shapes and forms. All matter is made up of tiny particles called atoms. But don't worry about that for now. Matter can exist either as solid, liquid, or gas. These are the three states of matter. Let's examine the properties of each state. A property is the way something is that we can measure. The physical properties that we'll be looking at are shape, mass, and volume. Mass is the amount of matter in an object. Volume is the space occupied by the object. Solids are easy to recognize. Rocks, fruits, pencils, and plants are all examples of solids. A solid object has a definite shape that does not change when it is moved or put in a container of different shapes. Solids only change shapes when forced, like when they are smashed or broken. Next, solids have a definite mass that does not change from place to place. And lastly, solids have definite volumes. If placed in a container filled with water, a solid will displace an amount of water equal to its volume. Liquids have definite volumes and mass, but they do not have definite shapes. Liquids will assume the shapes of the containers in which they are put. Water, Milk and juice are just a few examples of liquids. Gases. Gases have definite masses. An inflated balloon will weigh more than an empty one. However, gases do not have definite volumes nor shape. And just like liquids, gases assume the shapes of the containers in which they are put. And so in summary, solids have definite shapes, mass, and volume. Liquids have definite mass, volume, but no definite shape. And gases have definite mass, but no definite shape, no volume. Later on, we will see why the states of matter have these properties. Next, interconversion of the states of matter. Now, the three states of matter can be interconverted by either heating or cooling. When a solid is heated, it melts to give a liquid. This process is called melting and takes place at a specific temperature called melting point. When a liquid is cooled, it solidifies back into solid. This process is called freezing and takes place at a specific temperature called freezing point. For a particular substance, freezing and melting takes place at the same temperature. When a liquid is heated, it changes into gaseous state at a specific temperature called the boiling point. This process is called vaporization. When a gas is cooled, it becomes a liquid in a process called condensation. Both vaporization and condensation occur at the same temperature for a particular substance. For water, it's 100 degrees Celsius. Sublimation is the conversion of a solid directly into vapor without going through the liquid phase. For example, iodine crystals vaporize into purple vapor when heated. On cooling, the vapor condenses back into solid state directly. This is called desublimation or deposition. Now the chemistry laboratory. Chemistry involves practical procedures called experiments. These are conducted in special rooms called laboratories. The laboratory provides a conducive environment for experiments and also ensures the safety of the users and that of the environment. Reactions themselves take place in special vessels or containers called apparatus. There are many apparatus, each with specific use and come in various sizes. Most apparatus are made of glass. Why? First, glass is an inert material, which means it does not react with most chemicals. Secondly, the smoothness of the glasses make them easier to clean. And finally, the transparency of the glass allows one to see the reactions taking place inside. Let's look at the various apparatus and their uses. Now, one apparatus that we need to pay special attention to is the Bunsen burner. The Bunsen burner is the main source of heating in the laboratory. It consists of three main parts: the chimney, the collar, and the base. The chimney is this long metallic cylinder with an air hole near its lower end. It allows the gas up from the inlet to be ignited at the top. The collar is this metallic ring surrounding the chimney at the lower end. It has a hole of equal size to that of the air hole. It controls the opening and closing of the air hole. The base is the thick metallic material with the gas inlet. It provides a firm and steady support. The gas inlet is usually connected to an external source of laboratory gas by means of a rubber tubing. The air hole allows air to enter and mix with the laboratory gas, usually methane. This way, there is complete combustion. When lighting the Bunsen burner, start with a closed air hole, and then connect the gas inlet to the external source of laboratory gas. We get a spark and open the gas. Notice that when the gas is first ignited, the flame produced is large, wavy, and with a yellow color. This is called a luminous flame and indicates inefficient combustion of the gas, and therefore a lot of unburnt carbon is being produced. When we open the air hole, air enters and mixes with the gas in the chimney. The mixture of air and gas burns with a nice blue flame. This is called a non-luminous flame and indicates complete combustion of the gas. There are no unburnt carbon being produced. A non-luminous flame is a clean burning flame. Never use the luminous flame for heating purposes in the lab because it will produce a lot of carbon or soot, which will make the apparatus dirty. A non-luminous flame is hotter, and this is good for heating but not lighting. When you look closely at the non-luminous flame, you can see three zones. The almost colorless region just at the top of the chimney, which is made up of mainly unburnt gas. The green-blue zone contains partially burnt gases due to insufficient air supply. In the outer pale blue zone, where there is complete combustion of the gas due to sufficient air supply. The almost colorless region is relatively cold because it contains mostly air and unburnt gas. The hottest part of the flame is just at the top of the green-blue zone, where air is now fully mixed with the gas. If you place a wooden splint at this point of the flame, it will produce this kind of a burning pattern. The unburnt region is the region that was in contact with the almost colorless zone. But if you place it up here, this will be the burning pattern. You see, the middle part is what was in contact with the hottest part of the flame. So you should not let the almost colorless zone come into contact with what you are heating because it's relatively cold. The best practice is to always place the item being heated just outside the tip of the green-blue zone because it's the hottest part of the flame. Here, we can see a porcelain crucible being heated in the Bunsen flame. Again, notice how the crucible is placed at the top of the hottest zone. And see how the underside of the crucible is red hot, indicating that it's being heated properly. Now, if you look at the luminous flame, you will see four regions. a thin outer pale blue region where there is complete combustion due to air supply from the surrounding. A luminous bright yellow region consisting mainly of tiny particles of unburnt carbon. This is the region that produces light and makes the apparatus dirty with soot. The almost colorless region consists of air and unburnt gas. And a blue zone at the bottom of the flame, where there is complete combustion of the gas due to air rising from the surrounding lower regions.
Let's put down the chemistry textbook for just a second and grab the history book. Which ancient civilizations are you learning about? Egypt? China? Rome? All of the ancient civilizations we still talk about today have at least one thing in common. They harness the awesome power of chemistry. Let's begin in the Stone Age. For thousands of years, early humans wandered the earth. Using stone tools and weapons, they grabbed what food they could find and huddled together for warmth. Then our ancestors discovered a very, very important result of certain chemical reactions: fire. Fire was great! You could cook food over it, you could keep warm, you could stay awake later plotting hunting strategies thanks to the light it provides, and you could keep hungry predators at bay. But early civilizations figured out one of fire's finest features. You could use it to make stuff out of other stuff. As early as 6,000 years ago, Egyptians used copper to make tools. They figured out that if they exposed copper ores to fire, they could extract the precious metal and pour it into molds. Archaeologists have found copper pins, chisels, needles, and other artifacts all over Egypt. Egyptians were also known for their colorful paint. That famous Egyptian blue is believed to be the first synthetic pigment, dating back to 3000 BC. Using crushed natural chemicals, or mineral salts, ancient Egyptian painters created vibrant murals in the tombs of the pharaohs.